hear me right?
Yes, and we can see your screen. Yep.
Cool.
Great.
Okay.
Thanks.
Let me open also. Yeah, okay. So as Scott mentioned, yeah, my name is Federico Lopez Armengol. I'm a postdoc here at RIT, and I'm a part of the ThinkTank collaboration. Yeah, I'm going to talk about the handoff, the post-merger handoff. This has really been a team effort, so yeah, I'm here talking on behalf of the entire collaboration. Okay, so let me start by defining what's the handoff. The handoff is a set of routines to transition a simulation of a binary neutron star or black hole neutron star post-merger from the Cartesian AMR grid, where they are usually made, to a more suitable grid to the new geometries of the system. That's schematized in these plots, where we have a merger in a Cartesian AMR grid. In the collaboration, we perform these simulations with Illinois GRMHD or SPRITZ. And here we have a post-merger in HARM3D. There is a code well tested for accretion disks simulations, and that most importantly can handle arbitrary grids. So here I'm showing what I mean by a more suitable grid. In more detail, by more suitable grid, I mean, well, we know that momentum is better conserved in the direction of the cell lines. So we want a grid with a spherical topology to better conserve angular momentum. These simulations in Cartesian coordinates usually make use of high resolution of 100 or 200 meters, and that's not enough for solving the MRI or the turbulence. So we want to go to high resolutions. It's hard to tell a resolution of this grid because it's very flexible, but you can think of it as an effective resolution of 50 meters at the disk region in DR. At the same time, we want to focus the resolution where the physics is happening, particularly at the disk close to the black hole. But yeah, as being pointed out in early in the morning, we don't want to de-resolve the jet. So further out, you can see that the grid transitions to a parabolic profile, and we focus resolution in the jet region. Then we also want a grid with a much larger domain, as already also Uri pointed out early this morning. And this grid goes out to 10 to the 5 kilometers. This will allow us to do very long simulations. Okay, so how can we do this transition? This is the workflow of the handoff. We need to start with a proper merger simulation. And once the black hole has formed and we get to a time when we want to do the handoff, we shift to the black hole frame, both in coordinates and in the space-time gauge, considering the position and velocity of the black hole. In parallel, we need to design the grid where we want to transition, and we need to export the Cartesian coordinates of its cell center, faces, and corners. And with these tools, we proceed to interpolate all the primitives and the metric from the Cartesian AMR grid to the new destination grid. We use multiple orders in this interpolation procedure. That's because, well, high orders are preferred because they reduce interpolation errors. But since we are handing off MHD primitives that can have shocks, we keep also first order interpolation. And in this step, we just select the right order for the right grid functions in each cell position. Then we need to extrapolate the primitives and the metric. I told you that this destination grid is huge compared to the original grid, so we need to extrapolate the primitives and the metric. Extrapolating the primitives is further easy. We just use HARM3D atmosphere. But extrapolating the metric is a bit more tricky. This is great work done by Bernard Kelly. What we do is we do a spherical harmonic decomposition of the metric that we received from numerical relativity, and we do a fit of these components, a fit by a power law and a constant to ensure continuity. And once we have this fit, we use it to reconstruct the metric and use this prescription to extrapolate the metric all the way to the new outer boundary. Then some formalities: we need to transform the tensorial to the new coordinate basis, particularly the metric, the velocities, and the vector potential. And since Harm3D evolves the magnetic field with the fluxity algorithm, we need to calculate the magnetic field by the curve calculation. This is very important because this ensures that this magnetic field will not have dB violations because of interpolation errors, since it comes directly from a curve. And we also calculate the space-time connections for this numerical metric that we received. And yeah, that's it. Then we are ready to evolve the system in Harm3D. Let me show you the handoff at work. So this is a binary neutron star merger performed with Linus GRMHD. This is using an ideal fluid equation of state. These neutron stars are magnetized, and we just proceed to the merger in the Cartesian grid. And after, here we stop the simulation, we take some perspective, and we are going to transition to Harm3D. Okay, so this data set already lives in Harm3D. You can see that the transition is very smooth. And this is how the evolution goes already in Harm3D. Let's see the transition in a poloidal plot of the same simulation. And again, outside at least, it looks very, very smooth. I know you're probably a bit suspicious about this transition, so let me show you some more plots that are reassuring. This is the radial velocity as seen very far away from the merger of this same simulation. This is at time of handoff, and this is after 10 milliseconds evolving in Harm3D. Here I'm showing that there isn't any runaway or unphysical collapse. It's just expanding with 0.1 velocity. This is the entropy. I don't see any shocks, physical shocks from the time of handoff after 10 milliseconds evolving with Harm3D. This is the accretion rate that we calculate in Harm3D. You can see that it's, I don't see any transient, and it's converging to the reference value in the literature. Here I'm not showing new physics, I'm just showing that the run seems to be free of pathologies. This is the magnetic energy. We see a rise of the magnetic energy initially. In blue is the magnetic energy, and this is the toroidal and poloidal components. We see a dominance of the toroidal components on the magnetic energy. These are the MRI quality factors in theta initially. So here blue means that we have less than 10 cells for each wavelength of the MRI modes. Initially there are some blue regions, but after 10 milliseconds everything turns red, so we are resolving the MRI properly. This is the magnetization. The magnetic field is rather chaotic still, and we don't see any sign of an outflow for this first 10 millisecond, but again, that this was expected. And finally, dB, this is just to show that there aren't any violations of the solenoidal constraint. Okay, so future work, we're going to evolve this RAM for longer, see how it performs in the long term. And also we want to identify the effects of this new grid on the post-merger. We want to see how the higher resolution affects the MRI growth, the magnetic field amplification, turbulence, and the angular momentum transport. We've been performing some tests that hasn't been so smooth. Here you can see the accretion rate of a Fishman-Moncrief disk. And when we transition to a much higher resolution grid than the original run, we see a sudden growth in the accretion rate. We trace that, we trace that back to a growth in the boloidal component of the field. So if you want to discuss this further, let me know. I would be very interested to know your point of view. And then, of course, the main motivation of the collaboration is to hand off a realistic simulation with realistic equation of state to HARM3D plus NUC. If you're not familiar with this code, see the talk of Ari, Leo, and Lorenzo for IGM and Spritz. And here I can show you already some snapshots of a handoff of a realistic handoff with a realistic equation of state. This is the density and this is YE. And remember, these data sets already live in HARM3D. So yeah, that's it. Thanks a lot.
Thank you, Federico. You are on time, maybe a little early, so we have time for questions.
Okay.
And we see applause. I really appreciated your slick slides. Those are really cool.
Mm-hmm.
Wolfgang has a question.
Yeah, I was a bit surprised by how this metric is extrapolated. So I would have assumed that maybe one matches some analytical fall off, but just extrapolating the local gradient seems a bit dangerous. So did you check that this is even still a good solution of GR in terms of constraint violation, and or do you have some very unphysical gravity field far away from the original domain? So this, in particular, this n, is that also a fitting parameter, this fall of power, or?
Hi, this is Bernard, because I was doing this. So to answer the earlier part of the question, I didn't check constraint violations with what I was doing, but this so that is a 3-parameter fit. The n was not pre-specified, though it was always a positive number as put there, and the extrapolation started. This fitting happened within a region fairly far out in the original numerical domain. So it took in terms of m, like between 200 and 500 m in radius. So it was well, it's well outside the strong field region, and all the fields were falling off with that kind of, or some kind of radial dependence anyway. So it would be good to do an extra check of constraint violations, but we were able to verify that the system certainly did show Kerr-like fall off of all fields.
But still at n should be approaching some known value at large radii, and at those large radii, it's probably pretty exactly that already.
Oh, yes,
and
I see what you mean.
The other strange thing here is, I'm not sure if A, B referred to spherical coordinates. If yes, I would expect different fall-off behavior for example, RR or R theta or something. If they do refer to Cartesian, then this is sort of mixing together stuff with different fall-off behavior.
I agree. This is Cartesian, though. It is Cartesian. And so from that point of view, it is a little strange because you're using a kind of a spherical polar basis with individual components that are Cartesian, but it seems fairly robust, is all I can say. But yeah, it's possible you could bring better insight into these terms, and in general, you could probably, if you weren't allowing for instance, the possibility of, say, gravitational radiation with quadrupoles that are kind of polluting this region, then you could probably just specify a very, very clean fall-off at large distances. We wanted something reasonable, but it's not impossible that something strange and very low amplitude happens further out, but still well behaved.
Okay, thanks.
Great. And we can discuss this further in the chat or in the discussion period in the afternoon. Let's thank Federico again. I think maybe we should move on. And the next talk is by Vasilios Neves. And